suppose there are some error and main trajectory of the bunch or bunch centroid is not going on the design trajectory, then we have some mechanism to steer it. These are particularly very tiny dipole magnets. So these dipole magnets can also be used to transversely scan the trajectory of a bunch. So in this scan method, basically both the bunches are transversely scanned over each other.
Okay,
Okay.
like
Then
transversely
they,
passed over each other.
yeah. And then they count the number of events as they overlap. They
Ah,
steer.
I see.
And by this, they calibrate the luminosity. But more detail, I don't know. I just know the basic principle of this.
Okay. Yeah, maybe I can read a paper about it later.
Yes.
So actually, because right now I'm at CERN and this heavy ion collision is going on, and
Yes.
we are having this Vandermeer scan.
Yeah,
That,
this is very
yeah.
old method actually.
Hmm.
Vandermeer itself means it was a person. It is a great scientist, actually, Vandermeer.
Okay.
Uh, some cooling method of emittances are also was invented by him, basically.
Okay.
So Vandermeer was a very great accelerator physicist, and he devised this method, and still it is going on. It is very old method. Means, if I remember correctly, Vandermeer worked in 1970s or in that decade, and still this method is. There are certain definitely limitations of this method because when bunch scans takes place, there are beam forces. Means one beam and other beam exerts coulombic and magnetic interaction with each other
Yeah.
that actually distorts the bunch shape.
Yeah.
So definitely this scan is giving some biasing, measurement biasing due to this bunch shape. So there are some correction method also devised for this Vandermeer skin, but definitely I don't know details of those correction and how actually those are implemented and like that. But in general, this is steering of the bunch and making it overlap over each other, and
Counting the
gradually as
events.
the overlapping is increasing, they count the number of events by detector. And number of events is definitely proportional to luminosity. So in this fashion, they actually measure the luminosity.
So that, I mean, so just to get the idea, if whatever the collision is happening, it is the maximum that they are getting, or is it?
Yes,
Yeah.
definitely.
To just make sure.
And some analytical formula are also available for only Gaussian distribution. If you have both the bunches are Gaussian distributed, then there are some analytical formulation is also there. However, in beam, there may be a different distribution than the Gaussian. So definitely some numerical fitting, etc., has to be done.
Yeah. Thank you, sir.
Because distribution can also be measured using some wire scanner or wire grid methods. So distribution can be obtained via other methods and then fitting can be done.
Okay, not only that, actually, if the beams are well separated, then the distribution may be Gaussian, but when they are coming very close to it and overlapping, then that Gaussian distribution will be disturbed. But as he said
Yes,
that
definitely.
there will be some corrections for that. and that has to be applied. But corrections, are already always approximate.
Yeah. Thank you, sir. So now, I think if Dhanush and Mohit have any question, they can ask.
Mohit has asked those questions, and I prepared
Oh, okay,
slide
okay.
by that question.
Yes, sir. If you
So
want, you can share. Uh,
okay, I'm just sharing it.
okay.
Is the screen visible?
Yes, sir. We can see. Yeah, we can see the.
Okay.
You can go to the PPT and maybe
Yeah.
full screen if you want. Yeah.
So this week, mainly the topics which were covered in lectures were equation of motion. We set some equation of motion of the particle in accelerator coordinate system, basically, and then how dipole magnets and quadrupole magnets can be used for focusing, or what is the focusing and defocusing effects of the dipole and quadrupole magnet. And then each magnet can be represented by some transfer matrices, then how to obtain those transfer matrices of the magnets. These topics were covered roughly in these three lectures. So focusing of the dipole magnet at the edges, the question was related to this one, so I prepared some slides. Suppose there is a uniform magnetic field, because it is a dipole magnet, so magnetic field in the space will be uniform, and the direction of the magnetic field is perpendicular to this screen. So definitely if a charged particle is launched whose velocity vector is in the screen, in the plane of screen, then it will make a complete circular path. Suppose this is the desired path, design path, or desired orbit, or design trajectory, whatever you want to say it. So this is the path which we want to intend, which we want, all the dipole magnets are set to design or obtain this path. This has certain design radius or radius of curvature rho, and this is the center of the circle. I have made some dark line on this circle. This is the arc. I'm assuming that magnet is only of this size. So actually the path inside the magnet is only this arc, and rest of the circle is shown on that. This is the arc of this larger circle. So if magnet is of this size, there will be arc of this radius of curvature rho. Now suppose some particle is deviated from this design path. Let us suppose that this is here. So this will make also a circular path, because this is a uniform magnetic field. So every particle which will pass through this magnetic field will make a circular path. Only what will happen if we consider the same energy of this particle as of the design path, then there will be only a shift in the circle. And that shift in the circle means this center O for the other circle will be shifted upwards in this case, and this will make also a complete path. So I also make a dark segment which may be inside the magnet. So these are two paths. One is the design one, which is shown in some red type of color, and in the violet type of color, it is shown some deviated particle. So we, in accelerator coordinate system, design path itself makes the coordinate system. So distance of this deviated particle is measured with reference to this design path. Say this is x0 at this location. Towards the entry of the magnet, say this is xi, I subscript is initial, and at the exit xe, which we measure from here. So you can see that xi and xc are smaller than x0, means a path or particle which is deviated more at this location is coming towards the design path. Means some type of focusing is taking place. So now on the right side, I again draw this picture, and now we make a sector of this circle, sector from the design circle, because we always make magnets with respect to design path. So design, so on the design path, we have some sector, say OC and OD. Now AB is the design path inside the magnet, and CD is the design path in the of the deviated part. CD is the path of the deviated particle inside the magnet. So now you can see that when it exits the design path or particle on the design path at its velocity component in this direction, velocity in this direction. This is just the tangent of this circle at the point B. So at exit, this is the direction of the design path. And the particle which is deviated, we can again obtain the direction of velocity by taking the tangent, and you can see that this is coming towards the design path, means some type of focusing is taking place, and this is only because the deviated particle is spending more path length or traveling more path length inside the magnet, so it bends more. It seems like this, although both are only a shifted circle. So by that shifted circle, we get basically the focusing at the exit. And this, because we are obtaining through a sector of the circle, and this is known as sector magnet. So this is the focusing effect of the sector magnet in horizontal plane. Now again, we see if orientation of these sector edges are altered. Now suppose we make the magnet like this rather than a sector. Means we have oriented our edge in this fashion at the entry as well as at the exit. Now the path of deviated particle from C to E and F to D are not inside the magnet. They are outside the magnet, because magnet starts from E and ends at F. Although design path is not different from previous one, because we have chosen the magnet to keep the design path same, because focusing and defocusing effect are seen only on the particle which are deviated from the design path. So design path should not be altered. So we are taking a different type of orientation of the magnet, and we are looking what is happening to the deviated particles. So now you can see again the design trajectory has the same tangent at the exit point B, means direction is not changed. However, for the deviated particle, now we will draw the tangent at F rather than D. So this tangent is not now in the same direction as of the previous one, and you can see that some defocusing effect compared to sector magnet has taken place. Means by orienting our edges to different direction, defocusing or focusing effect can be generated. Now this was the problem 4 of assignment mine, which was asked that how the answer is C in this case. We will now analyze the problem step by step. The last slide which I show has like this edge. This red curve or red axis is along the sector edge. So this thin line is showing you the sector magnet. If it had been a sector magnet, and this is the edge of the magnet which we are using right now, means the edge of this magnet is oriented from the sector direction. The design trajectory is itself is same as in the sector magnet. So this is the design trajectory coming here, entering in the magnetic field, and now it is having some curvature due to magnetic field. At the entrance, the direction of velocity is just the tangent of this curvature here, so it is just in this direction. And this is the edge of the sector magnet. If it had been a sector magnet, this should be the edge. Now suppose we orient completely this picture by some angle to make this sector exactly vertical. So now this will be the picture. Instead of this direction, the direction of the incoming beam will be there and edge will be like this. I just didn't change anything in the picture, just oriented it, just rotated it with some angle. So this is the picture rotated. Now suppose instead of North Pole and South Pole, we switch over it. Means if suppose in this picture, North Pole is above the screen and South Pole is below the screen, and particles charge sign is that it is making some trajectory like this. Now we switch the magnetic poles. So this trajectory will be now in anti-clock direction rather than clockwise. So this anti-clockwise direction will be there. In this picture, left picture, we have seen that this will give some defocusing effect in the horizontal plane, this orientation. It means it will give some focusing effect in the vertical plane. We already have gone through the lectures that if some magnet is producing some focusing effect in the horizontal plane, it will generate defocusing effect in the orthogonal plane. So this is defocusing effect in the horizontal plane. So definitely this will generate some vertical focusing effect in the other plane. Now for making again, when we switch over the poles or direction of the magnetic field has been switched over. Now if we want to make it focusing again, in this orientation, this will be now defocusing in the vertical plane rather than focusing. If we want focusing in the vertical plane, we have to orient the edge in reverse direction. Means we have to make the edge in this direction. So this direction with this trajectory will make the vertical focusing. And this is the option C, which is the answer of this problem. I think now this is clear to everyone. Now there are some problems related to magnetic rigidity and what is the kick angle, what is the K in formulation, what is the unit of quadrupole strength K and all that kind of thing. So we just refresh those things here. If suppose you have given some energy and particle, how to obtain the magnetic rigidity? Magnetic rigidity shows that if there is some bending, some dipolar magnetic field and particle is going through that magnetic field, what will be the radius of curvature? So magnetic field multiplied with radius of curvature give you the magnetic rigidity, and it is directly proportional to the momentum of the particle. That's why it is shown as magnetic rigidity. How rigid is the particle against the magnetic field? So first obtain the relativistic ratio gamma. So gamma is basically total energy of the particle, which is kinetic energy plus rest mass energy of the particle divided by rest mass energy of the particle. So you can get easily the gamma with the given data. Using this gamma, you can calculate the beta. Beta and gamma are related with this relation. Beta is square root of gamma square minus 1 upon gamma. So you can obtain beta very easily. And now using this beta, you can calculate P by Q. And P by Q itself is magnetic rigidity B rho. B rho will be in Tesla and meter. If you will go through beta, which you have calculated here, E in electron volt, remember here it is E is total energy, means kinetic energy plus rest mass energy of the particle, and you put this value in electron volt and divide it by speed of light in meter per second, you will get the result in Tesla meter. And just P is equal to beta E by C, it is through the relativity. So in this fashion you can get magnetic rigidity if you know the energy of the particle. Now, if you know the particle is highly relativistic, suppose we are talking about the 300 MeV electrons or 400 MeV electrons, you know that beta is close to 1. So you can directly get E by C and you will get the magnetic rigidity of that particle. Means suppose 300 MeV electron is there. So 300 into 10 raised to 6, that is EV, divided by 3 into 10 raised to 8, this is 1. 1 Tesla meter is the magnetic rigidity of the 300 MeV electron. Means if particle goes through the 1 Tesla magnetic field, the radius of curvature will be 1 meter. Now, how to calculate the change in angle of the trajectory when it passes through the magnetic field? Magnetic field may be of the dipole magnet, quadrupole magnet, or like that. So what will be the change in angle of the trajectory of a particle when it passes through this magnet? So change in angle, we say sometimes this is the kick angle because particle gets a kick. So this delta theta is B delta L upon B rho. Delta L is the path length over which we are or particle is passing through. This means this is the length of the trajectory of the particle inside the magnetic field. Definitely delta L should be tends to 0 and we have to integrate it to get the correct result. But in thin lens approximation, we can take delta L of the magnetic field length as the magnetic field and B over the magnetic field, and B rho is again the magnetic rigidity, which we have seen how to calculate it. So first calculate the magnetic rigidity, which is in the denominator as described in the previous slide. Then use above formula in thin lens approximation, which can give you the change in angle. So for dipole, B is constant. We will put B here directly use about relation by putting the values of B and delta L. So change in trajectory angle of a particle when it is passing through the dipole magnet is very easy. Just use directly this relation. In case of quadrupole, we know B itself changes with distance from the design orbit. Means By is equal to Gx. G is the gradient of the magnetic field. In dipole magnet, B is 0. In quadrupole magnet, G is constant. Means gradient is constant. The quadrupole magnet is characterized by the gradient of this magnet. Means how much magnetic field is changing in how much distance. Means 10 Tesla per meter is the gradient or 20 Tesla per meter is the gradient. So at this B, we will put the value of Gx. So this will be the horizontal kick because we are getting the kick in the horizontal direction. If we will use Gy, then we will get kick in the vertical direction. So Gx delta L upon B rho. Now using above relation, if you have provided the gradient of the magnet, you just put the values, and you were also given the value of x in the case of quadrupole magnet, and you will get the change in the angle. Instead of G, if quadrupole strength K is given, then what will we do? K is G by B rho. Now from here you can calculate the unit of K. This K is known as quadrupole strength. So G is in Tesla per meter and B rho is Tesla into meter. So your Tesla will be cancelled out and you will have the K just 1 by meter square. So unit of the K is meter minus 2. So this is the quadrupole strength. Sometime literatures actually multiply this delta L also, which is known as integrated quadrupole strength. In this case, G by B rho into delta L means unit of integrated quadrupole strength will be 1 by meter. So 1 by meter square is the normalized quadrupole strength, and 1 by meter is the unit of normalized integrated quadrupole strength. So actually in accelerators, we describe the optics using this K rather than G because it makes the optics description independent to energy. Energy is here B rho. B rho is magnetic rigidity which is proportional to P, means it is taking care of the energy. So, while a gradient is normalized by the central energy or design energy of the particle, so this K defines the optics independent to energy. Means if I am saying that K is 2 meter minus 2 in my optics, then if you are using 5 MeV proton beam, just calculate what is the B rho of that 5 MeV proton beam and multiply it with K, you will get what is the required gradient in the quadrupole magnet. So in delta theta, if K is given, at this place G by B rho, we can put K, then X and delta. So if these numbers are given, in assignment, unit of this K was asked, and if this number is given, then you can calculate the kick angle of the quadrupole is also easily. So if you have any other doubt in the assignments, then you can ask.
Thank you, sir, for the detailed explanation. Yeah, Mohit, go on.
Dhanush has left, perhaps.
Yeah.
So Mohit, these questions were asked by Mohit. So Mohit, now is this clear or some doubt is there? Even if you have certain doubts, you can ask in the forum also. And if you are presently you have some doubt, you can ask here also.
Are you there, Mohit? Oh, okay. It's giving thumbs up.
And Rohit Kumarji, I will see more detail of the Wandermere scan. I will also learn,
Yeah,
and
yeah.
then we will talk to each other.
Yeah, sure, sir. And also, you can send these slides. I can upload them.
I will share these slides.
Yeah. Yeah, I mean, right now it's very exciting here. uh, because we are having this heavy ion collision after 5 years. Last time we had some issues in our tracker in CMS. So I mean, we cannot. I mean, we didn't have uh, particles below 500 GeV. So this time we have fixed that, and we are hoping to go below like around 300 GeV. So let's see. Mohit has
shared some jam file.
Okay. What is it? It needs access. So Mohit, can you give me access so that I can open it? What is it, by the way? Oh, okay. I think he done it by mistake. Okay, no problem.
It is perhaps whiteboard.
Yeah, I understand. It's okay. So you don't have any more questions, Mohit? I guess not.
So Rohitji, presently what is the status of high luminosity run of the LHC?
So it is planned for the run 5 and run 6. Currently, I think testings are going on, but I'm not involved in them. So, but yeah, things are going well, I guess. And also, CERN is planning to have this future collider.
Yeah, there's this 100-kilometer circumference
Yeah.
FCC.
So one of undergrad student who she was doing a project with us. She recently joined a certain PhD fellowship, and she will be working in simulations of that FCC. But I don't know. I'm not sure that. So it is still under the investigation phase. I mean, feasibility phase or something.
Yes, yes,
Yeah.
that
So.
is. And before that, I think before SPC, click should be completed. No?
Click. Uh, Click is the
Means
linear
what is going
collider.
on about the click? We don't hear much news about the click nowadays. Few years back, the project was very hot. Actually, click everywhere. Click was there. The click test facility has been built and like that, and it is competitor to ILC also. But presently, we don't listen so much about the click.
I don't know. I see the click facility. I mean, on my way to our CMS center, I see the click facilities there, but I'm not sure if people are working or not.
Actually, I have my PhD in the click test facility.
Oh, that's great.
So I'm asking what is the present status? My PhD was completed in 2014, means uh, Dr. Pitamar Singh ji was my kind guide actually in this
Oh,
PhD.
okay.
So he's my Gurudev.
Oh, nice.
So, actually, under his supervision, I completed. One of the optics was designed by us, and actually, that is deployed there in the click test facility. Before the CLAX area, the transport line was designed by us, which was basically a bunch compressor. So just I was curious to know how the click is going on right now. Because my PhD is completed 7-8 years before, long back,
So,
7 to 8 years.
so they have not taken any data so far?
No, 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 no. They have actually click test facility has produced the result which were desired.
Okay.
Means 100 MeV per meter gradient has been obtained in the cavities, and some beam, test beam is also accelerated there. But that was the test facility, means proving the test principle, proof of principle type of facility was there.
Yeah.
They have demonstrated there's the concept of the click will work. But what is about click itself? I think the pace is very slow in that project, maybe due to some other problem, budget problem or like that. I don't know.
No,
But
I think, Amlendu, that is not a priority now at this moment.
maybe
Because
because ILC is also very slow.
upgrade of this LSC is a priority.
Yes, yes, definitely. But I think ILC is also slowed down, no?
ILC, we don't hear about it now.
Yes, both the means lepton colliders has been slowed down. What happened? I don't know.
Yeah, ILC at least the location is decided. It will be in Japan.
Yes, it will be Japan.
I think we have one student, Jagjeevan Kumar.
Yes, Jagjeevan Kumar.
So, hello
So if
Jagjeevan.
Jagjeevan
Yeah.
Kumar has any doubt, he can ask here. Jagjeevan, if you have any doubt.
Sorry, good evening, sir.
Yeah,
Good
hi.
evening.
Hello. Yeah, yeah.
Yeah.
Yeah, good evening, everybody. No, no, sir, I haven't downed. I just check it. So, what was happening over here? So, I was checking over there.
Yeah, so basically here what we do is if you have any doubt in the previous week lectures, you can ask here. The instructor of the course are here and they can answer you in detail. So,
Yeah, I got it, sir. I
oh,
got it.
okay, okay.
Yeah.
Uh, uh, Rohit, next Saturday,
Mm-hmm.
I'll show
Mm-hmm.
one slide where uh, in the lecture we made one error,
Mm-hmm.
which I will be telling that what error that was. Of course, in the first one, when I was discussing about DC accelerators, I told that.
Okay.
I will repeat it again because uh, in that slide there were two errors. One I told and other one I am not very clear myself.
Okay.
And so I have telephoned many people
Mm-hmm.
to clarify that point to me. And as soon as I get the answer, I will be talking about next Saturday. I
Okay.
mean, that's a
Okay.
very interesting thing.
Okay. Okay. Sure. Sure. You can share the screen and so the slides.
See, I can tell you the problem. See,
Mm-hmm.
when in the DC accelerators,
Mm-hmm.
one of them, there are three, four methods to calculate the voltage, terminal voltage.
Mm-hmm. Yeah.
And one of the method is that we put lot of resistances. So there is a resistance change across the column section
Mm-hmm.
and a certain current passes.
Mm-hmm.
So we suppose the total resistances R and current passing through that is I.
Mm-hmm.
Then we say IR is the voltage on the terminal.
Mm-hmm.
Now, how do we measure this current? Where we put the monitor, this current emitter, basically, where exactly it is located. So I telephoned some of my colleagues
Mm-hmm.
who are now working. I asked them that where exactly is the meter put in. So normally, because the current passing through is same in all the resistances, because there's a resistance chain. So what is normally theoretically done is that in the last portion between ground and the resistance, there is a meter.
Mm-hmm.
So the current is passing through. Now the problem is that this meter, which is an emitter, one end is at ground potential, other is at the voltage.
Mm-hmm.
Now these meters are not meant to extend the voltage.
Okay.
So how we take care of that safety aspect of the meter? So that somebody told that he will look at it and tell me.
Okay.
This
This
is a
is
very
interesting.
technical question.
Yeah.
Nobody has ever bothered about it.
Yeah. Yeah.
So
It
I
is
thought
very.
I'll clarify in next Saturday. By that time, I will find out the answer to it.
Okay. Okay.
And the other one was the plate which we put in the terminal. That in fact in the first clarification lecture I told That is not continuously is not touching the pressure vessel, because pressure vessel is grounded.
Yeah.
So if this plate continues and touches both sides on the grounded pressure vessel, there will not be any voltage. So this plate on which the high voltage is put in is only in the center, and remaining side, both sides are open.
Mm-hmm.
So that means this high voltage terminal is just standing like like a is totally independent. So
Understand.
that I will
Suspended
give.
kind of thing. Somehow
Yeah,
suspended.
this is like a जैसे वो नॉर्थ साउथ इंडिया में होता है ना, एक गेम होता है ना जिसमें वो चढ़ते ऊपर में.
Mm-hmm.
But I do not want to name his religion. It's like shivling,
Yeah, yeah, yeah.
but that will not be a good example.
And like a
So
pillar.
that is, yeah, that is it's a pillar basically. It's thumb.
Mm-hmm.
So it's not connected. So in the terminal, it is not connected anywhere.
Mm-hmm.
While in the pictures which I have shown,
Mm-hmm.
I should have shown that dotted instead of continuous one. So that I will make that picture once again and show it so that people realize that should not be taken on the right.
Okay, sir. Sure. So Dhanus has joined. So hi Dhanus, you have to ask anything?
No, sir.
Oh, okay.
Thank you.
Okay.
I think now we will have only two more sessions
Yeah.
because this
Yes,
course
sir.
will
After
end on
this,
14th October.
After this, we'll have
So,
two more.
my request is that next 2 weeks,
Mm-hmm.
as many people as possible should attend it so that all the doubts can be cleared.
Yeah.
And on the last Saturday,
Mm-hmm.
I will request all my colleagues to be present,
Mm-hmm.
but it should not be disappointing, because when only one participant is there and four of us are there, it looks very disappointing. So my request is that as many people as possible should attend that and have all the doubts
Mm-hmm.
cleared that time, and we'll all try to be there on the last Saturday.
Yeah, maybe we can request someone from NPTL to send a message around that.
Yeah,
Yeah.
I'll send a email to that person who sends
Mm-hmm.
this notification
Mm-hmm.
that he should
Mention this.
mention it, that will be last, and I
Mm-hmm.
think all of us will be present
Okay.
on that day.
Okay, sir. If we don't have any more question from the students, and maybe we can end today's session and meet next Saturday.
Okay. I have mailed today's
Okay.
PPTs to you.
Thank you, sir.
Okay.
Okay, then see you. Bye.
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 Sorry.